This is 2.5 Lewis diagrams, and our outcome is I can represent a molecule with a Lewis diagram. So to draw Lewis structures for molecules, a couple of rules to follow. Hydrogen must share 2 electrons. The sum of the shared and lone pairs for carbon, nitrogen, oxygen, fluorine, they all must be 8 in octet. And usually the elements in groups 14, 15, 16, and 17 also follow the octet rule. So whenever we want to draw a Lewis structure, we need to sum the total number of valence electrons from all the atoms. And then we're going to draw a skeleton structure connecting everything with single bonds. Then we distribute remaining electrons to satisfy the octet rule. And we might take some of those electrons and distribute them into bonds in order to satisfy that octet rule. So the first question here is, what is the Lewis structure for a nitrogen atom? So the electron configuration for nitrogen gives us 5 valence electrons. So remember that there's a pattern. You go top, right, bottom, left, top, right, bottom, left. So we fill it in that way because that's how electrons fill in the energy levels of the atom. So the number of unpaired electrons gives us a hint about the number of bonds that this needs to form. So nitrogen needs 3 more electrons to satisfy the octet rule. So if we think about a molecule that is made from just hydrogen and nitrogen, hydrogen has 1 electron and nitrogen needs 3. So it makes sense that I would need 3 hydrogens for every 1 nitrogen. So why do we only think about those valence electrons whenever we draw a Lewis diagram? Because those are the only ones that can form bonds. Those are the only ones that are able to overlap with each other without the electron-electron repulsion or nuclear repulsion being too strong. This allows them to be at that ideal distance where that potential energy is minimized. So the next question is to draw a bunch of molecules. So let's go ahead and take a look at that. And we'll start with HF. So hydrogen is going to have 1 valence electron, and fluorine is going to have 7. So we probably have a good sense. We probably have this one memorized as well. But let's go through it like we don't know what this is going to be. Because eventually you'll encounter molecules where you don't know what it's going to be. So I have a total of 8 electrons here. So I'm going to start just by connecting the hydrogen to the fluorine with a single bond. So that's my skeleton structure. So of those 8 electrons, I've placed 2, so now I have 6 left. So I'm just going to distribute those 6 around the fluorine. I don't need to distribute any around the hydrogen because hydrogen only needs 2 electrons to be stable, and those are in the bond. So I put those other 6 electrons around fluorine, and now fluorine is stable. It also has a full octet. Okay, so the next one we want to look at is oxygen. So oxygen is going to have 6 electrons. 2 oxygens means 12 electrons total. So I know that I'm going to need to attach these 2 oxygens together with at least a single bond. Most of us probably know that this is a double bond from experience, but let's go about this like we didn't know that. So in that single bond there, I've placed 2 electrons, which means I have 10 left. So I'm going to go ahead and distribute those around those oxygens until we get octets. So 1, 2, 3, 4, 5, 6. So that means I now have 4 left. And 1, 2, 3, 4. So now we have to check. Does everybody have an octet? So this guy over here, we've got 1, 2, 3, 4, 5, 6, 7, 8. So this side is good. 6 electrons, lone pairs, and 2 in a bond. But on this side, I have 4 plus 2 in the bond. I don't have an octet there. So what can I do to make it so that that oxygen has at least some access to 2 more electrons. Well, I'm going to take these 2 electrons here, and I'm going to move those into the bond. So I'm going to take this guy and move it into the bond and make this a double bond. So now I'm going to get rid of that. And now whenever I count, 1, 2, 3, 4, 5, 6, 7, 8. Now they both have octets. So this is how you would know that oxygen has a double bond if you didn't have it memorized. So the next one we're going to look at is CH4. So carbon has 4 valence electrons, and there's 1 of those, and hydrogen has 1 valence electron each, and there's 4 of those. So I have a total of 8 electrons. So anytime that you have hydrogen, hydrogens can only make those single bonds, so they're never going to be the central atom. So then when you have to choose between hydrogen or some other element, hydrogen is going to be forming single bonds. It will not be the central element. So in this case, it's going to be carbon. And I know that I have to attach 4 hydrogens onto this carbon, and I've got 8 electrons to do that. So I'm just going to start with my single bonds here. And after drawing those 4 single bonds, I've already run out of electrons. I have no electrons left. So now I just need to check if my atoms are satisfying the octet rule. So the carbon has 8 electrons around it, and each hydrogen has 2 electrons around it. So this is the Lewis structure for CH4 methane. The next one is a little bit different because it's an ion. So here we have NO+. So nitrogen has 5 valence electrons, and oxygen has 6 valence electrons. But that gives me a total of 11 electrons here. So here's where it being an ion comes in. Because this is the cation, that means that this molecule, this ion, has lost an electron. So I don't really have 11 here. I actually have 10. So I'm going to go ahead and connect nitrogen to oxygen with a single bond. And when I do that, I've used up 2 electrons. So now I have 8 left. So I'm going to start placing those. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm out of electrons. So now I need to see if everybody's octet is satisfied. And I can tell you that nitrogen is not. Nitrogen has these 2 up here, and then the 2 in the bond, which is a total of 4. So that means that I need to take some of these lone pairs of electrons and move them into the bond. So I'm going to move these 2 into the bond, make that a double bond now. I'm going to go ahead and get rid of them now that I've moved them into that bond. And now that gives me 1, 2, 3, 4 in the bond, 5, 6 with the lone pair, so that's still not an octet. So I'm going to go ahead and move another pair of electrons into this bond. So now we have a triple bond. And that triple bond gives nitrogen 6 plus 2, which is 8. Oxygen will have 6 plus 2, which is also 8. Everybody has an octet here. And since this is the ion, we're going to go ahead and indicate that by writing the charge. So here are a couple of Lewis structures. So for chlorine, the sum of the bonding electrons and the lone pair electrons, how is that consistent with the Lewis model? So that makes sense because if you count the lone pairs and the bonding pair, that gives you a full octet. 6 lone electrons and 2 bonding electrons. So this indicates a single bond. For nitrogen, is the sum of bonding and non-bonding consistent? Yes, because we have 6 bonding electrons in the triple bond and 2 non-bonding electrons on each nitrogen gives us 8 total. For H2CO, carbon has 4 bonds, so 8 bonding electrons, 2 single bonds, 1 double bond. So yes, it does follow. Also works for oxygen. It has 4 lone electrons and 4 bonding electrons, so it's like a double bond. So as far as your checklist to see if a Lewis structure is correct. So first we need to make sure that we have the correct total number of electrons. That should match the total number of valence electrons in the molecule. Are there 2 electrons around each hydrogen? And are there 8 around all other atoms? So now we can explore bond order and bond strength. So here are several molecules. Bond energy is the energy that is required to break this depicted bond. So based on the data above, verify that those structures are correct. So we've got H2CCH2, which I believe is acetylene. So yes, those Lewis structures work. Everybody has octets. The total number of electrons is correct. So what is the relationship between the bond order and single, double, or triple bond? So the bond order tells you the type of bond. 1 is a single bond, bond order 2 is a double bond, and bond order 3 is a triple bond. And that has 2, 4, and 6 electrons involved respectively. So looking at the data in the table, we see that single bonds are the weakest, and then triple bonds are the strongest. So if we look at like nitrogen or this triple bond here between these 2 carbons, much higher than what we have in our single carbon-to-carbon bond. So here I have the Lewis structures of several molecules here. So HF, HCl, HBr, and HI. So these are not going to be, these are in the gaseous state, so we wouldn't call these acids. These are gases, HF, HCl, HBr, HI. If we dissolve those in water, we would then call it an acid. So these are all bond order 1, and we see that as the size of the anion gets larger, the bond energy decreases. So fluorine is going to have 2 shells of electrons. Chlorine has 3, bromine has 4, and iodide has 5. So as the anion gets larger, the bond energy decreases. Now this makes sense if you think about it as a Coulombic attraction. As the center of positive and negative charge are further away from each other, we see that the distance is smaller in that Coulombic attraction equation. So considering the relative size, what trend do you predict in bond length? So the halides increase in size from fluorine to iodide, so the HX bond length should increase in the series as well. Here are several diatomic halogens. We've got chlorine, bromine, and iodine. So these are all bond order 1, and we see that as we go from chlorine to bromine to iodine, that the bond energy decreases. So this is again because these anions, these atoms, are getting larger, which means that they're a bigger distance apart. And in that equation for Coulombic attraction, the bigger the distance is, the smaller the attraction. So we can see that those require much less bond energy to remove them from that attraction. So the shorter the bond, the stronger the bond. The more energy is required to break it. So here we want to look at which bond is harder to break. We know that a double bond is going to be shorter and stronger than a single bond. we know that a triple bond is going to be stronger than a double bond. So here we're looking at a molecule of this type where X is either fluorine, chlorine, bromine, or iodine. So which bond would I expect to be the longest and the shortest? So I expect for the C to F bond to be the shortest because fluorine has the smallest atomic radius and iodide has the largest atomic radius. Which of these bonds would we expect to be the strongest? So again, the strongest bond is the shortest bond length. So that's going to be the carbon to fluorine. And the weakest bond is going to be carbon to iodine. So that means that we can actually measure these bond energies, and that's how we can confirm the structure of these molecules. So your reflection questions are to revise and finalize your checklist and explain the relationship between bond order, bond length, and bond strength in covalent bonds.